Yep.
Okay, cool. So I'm gonna go over a ring problem for you guys, just because a lot of you said you wanted to go through a problem in class and we didn't get to. So the basic setup for this, right? We know it's an electric field problem, so we can write out our electric field equation, and then we can draw our system. Now, there's a few different things you have to label here, and not all of them I think are labeled for you. So when you have a ring problem like this, right, where you have this inner annulus and an outer like diameter, you got to make sure that like you have both the bounds, right? So when we integrate over this sphere, right, this charged plate with some surface charge density sigma, where sigma equals the total charge Q over the area, the total area, right? And you can find the equations for that. That's all geometry for finding the total area, right? Two circles, you subtract. But we have to label some of the things on this image. So one of the things you have to label is this B. So this is just a constant distance to our particle point, B, right? This is what we're trying to measure. This is centered too. That's an important thing, right? That'll let us use some symmetry arguments. And we have this variable R. So this R is what we're going to integrate over when we integrate the area of this disk. And then we have this other thing, curly R. Now, I want to emphasize that R and curly R can change, right? Curly R can be like this distance, or it can be that distance. These are both variables that change as you change radially. Now, the difference between R and curly R, where curly R is in the equation here, this is the distance between the particle and the test point. So when I have R here, right, that's just going along the disks. That's a great way to describe how I'm traversing the disk, but it's a really poor way to describe how far away from the particle I am. So that's why we have curly R, and that's just the distance that is, and that's a placeholder. So we're going to replace that with something we can integrate over later. Now, to get into an integral form, we're going to take this and we're going to split it up into small chunks, right, so we can integrate over it. So we need some small dE, so some electric field contribution equals KQ, and this is going to be a dQ, so some small charge contribution over R squared. So these are pretty much analogous. This is just how you get it to become the integral that you want it to become. So then we have to figure out what dQ is. So in this case, we know that there's some density of charge. So if we take dQ, we can say that's actually equal to sigma times some small area dA. Now, we have to figure out what this dA is, and that's going to be a little bit of an issue. In this case, we are going to make a symmetry argument and say that, and I went over this in class, so I'm not going to dive into it super deep here, but you can say, right, that equal contributions from both sides cancel out the y components, so they're only left with an x component. And then, so every x component we can integrate over some ring, right? And over some ring, right, if we take a slice of a ring here, right? Since P is in the center of this, curly R is going to be the same value around here. And I can show you that actually. Because curly R is the hypotenuse of a triangle, right? So we can say, make this statement, right? So this is Pythagorean theorem, and I wrote the square root, so we're going to erase that. This is Pythagorean theorem, right? A squared plus b squared equals c squared, right? Because there's a square root there. So we know that that's the same value for any r, right? Because b is always constant. So if you choose some r, so choose some ring, you're going to have the same distance. So we know that every little piece of charge on this same radius is going to contribute the same amount to the x value, to the x direction electric field. So we can actually rewrite this as dE in the x. But to do that, we have to make sure that we're only taking the x component, right? Because this is the total, including the y. So to do that, right, we're going to have to define an angle theta. You can also do it directly, but we're going to define an angle theta, get a cosine, and then grab the ratio from that, and I'll show you how to do that. So let's say theta is here. And we know that we want, let's see, it's going to be So a trick in geometry, right? If we extend these lines, these angles are actually the same. And you can actually prove that really easily. So if you want to know why this is the case, I would encourage you to just work out the angles, and you can do a geometrical proof of this. It's really cool. But we know that these angles are the same, right? And our electric field vector is going to point along that line. So if we take the cosine of this, and I'm going to call it a dE, right? So some small electric field vector contribution. If we take the cosine of that, because right, that's what we're going to do over here. If we did cosine theta times this, we're going to get dEx. Then we have to figure out what cosine theta is. So cosine theta, right, is opposite over, or adjacent over hypotenuse. Which is, in this case, going to be b over, right, that's b over curly r, and we know curly r is this. So that's square root b squared plus r squared. So then we can rewrite dE as we can write dEx actually, right? Which is only the only thing we care about, right? Because dEy doesn't matter. So we can write dEx as k, and we're going to write sigma dA, and we're going to deal with the dA in a minute, over, this won't be a square root because, right, it's curly r squared, so you get rid of the square root. But then we also have another square root, so I'm going to say it's 3 halves. I'm going to combine these terms because we have a b over square root b squared plus r squared, right? But we also have square root b squared plus r squared here. So I'm going to combine these terms, and we're going to have square, or I'll put it to 3 halves, it'll be easier to see. B squared plus r squared to the 3 halves, right? So now we have this equation, right, which is great, but we still don't have a term we can integrate over. So what we need to do is get dA in terms of r. So we know we can choose small chunks of rings, so that's what we're going to do. We're going to integrate over rings, right? Now what's the area of some small ring? It's roughly 2 pi r, right? So it's the circumference times its width, so some dr. And that's something we can integrate over, right? So if we plug this dA, right, some area of some small ring into here, and we're going to get that have 2 pi r. I'm gonna keep the variables separate. 2 pi b sigma over, so that's just some constant, right? 2 pi b sigma times r over b squared r squared to the 3 times. And that is going to be what we can integrate. So then we can perform our integral and it'll solve out. And here you do u sub, and you'll get that r's change, and then you can just integrate u to the -3 halves.